Hey everyone, I am Jamie. I am presenting to you our work, Quantum Intuition XR, Tangible Quantum Mechanics Using Interactive XR Experience. I am presenting this work on behalf of my co-authors, Marven Wong, Matthew Brooks, Charles Tahan, and Myungin Lee. So to start with, quantum mechanics is famously difficult to learn, not because the math is impossible, but because the concepts are completely contradict with our everyday intuition. In classical physics, we can usually imagine what is happening physically, but quantum systems behave very differently. Traditional instruction relies heavily on equations, static diagrams, or simulations on 2D screens. However, quantum intuition does not naturally emerge from formal instruction alone. Students often learn the math without developing real conceptual understanding. So, what if we can create a museum experience to see a quantum computer from the inside, where users embody qubits, move to interact or entangle, and press a button to manipulate or measure? The integration of quantum mechanics with XR has gained traction as a mean to enhance understanding of complex quantum phenomena. A work in 2020 developed an interactive VR modules to manipulate simplified quantum circuits, and the benefits were found primarily in understanding single qubit circuit. Another relevant study in 2022 introduced a 3D virtual environment using co-spaces for teaching quantum computing fundamentals, and this provides students with an interactive quantum laboratory. And in 2023, Entangle VR offered an immersive narrative design tool using metaphors as inspired by quantum entanglement, and this emphasized experiential storytelling over physical accuracy. And while these systems are effective for illustrating core quantum concepts, they primarily rely on guided, representational, or configuration-based interactions. So as a result, users largely observe or configure predefined processes instead of directly engaging in an open-ended, dynamically evolving quantum system. So in this work, Quantum Intuition XR or QIXR, we aim to create an interactive, open-ended, and embodied exploratory experience that leverages XR to make quantum mechanics more tangible and to foster the development of quantum intuition. We introduce a scientifically grounded, embodied interface where users can manipulate qubits, apply gates, and dynamically trigger entanglement through spatial proximity, and all possible by real-time, mathematically accurate simulation. So this emphasis on fidelity, multisensory feedback, and embodied interaction sets QIXR apart as a novel educational platform for fostering quantum intuition beyond utilizing metaphor or symbolic abstraction. This is the schematic of our system. So the proposed system comprises quantum computing, input-output systems, and XR. Quantum computing includes block sphere, wave function, entanglement, and gates. Input-output system connects the XR domain with quantum computing, with graphic rendering, audio synthesis, and user interface. For implementation, we used MetaQuest 3 device, and the Unity game engine and programming language C# is used to develop the application. QIXR can be streamed through a headset wirelessly with Oculus Link, or experienced as a standalone offline application that runs on the device. So QIXR consists of 5 elements. First, qubit and block sphere. So each qubit appears as a floating block sphere, and when the qubit's state changes, the sphere rotates in real time. And next are quantum gates, and these are operations that transform the qubit states. We implemented 4 single qubit gates: automart, polyx, polyz, and phase S. Next are wave functions and entanglement. So the wave function is the mathematical description of a quantum state and governs how it evolves over time. When 2 qubits are far apart, their wave functions remain separate. When they overlap, this signals the beginning of interaction and possible entanglement. So entanglement occurs when 2 qubits become intrinsically linked and can no longer be described independently. And then finally, measuring turns quantum information back into normal information. For more technical details, please refer to our paper. So to validate the scientific accuracy of QIXR, we conducted interviews with 5 quantum physics experts. All participants held a doctoral degrees and had research experience in quantum science. So after experiencing the system in VR, they complete a 7-point Likert questionnaires and they participated in an open-ended discussions with us. So overall, the feedback was highly positive. The expert rated this system strongly for accurate representations of qubits and Bloch sphere, quantum gates, entanglement dynamics, and measurement behavior. So the median ratings were mostly between 5 and 7 out of 7, and this indicates a strong agreement that the system is scientifically grounded. Overall, the expert evaluation confirmed both scientific fidelity and educational potential of the system. To evaluate the potential of QIXR to support developing quantum intuition, we conducted a controlled user study of 24 participants. The group included 13 males and 11 females with a mean age of 25.3. 6 participants had a basic understanding of quantum concepts, while the other 18 had no prior quantum experience. So participants were randomly assigned into 2 groups of 12. The first group was the VR-based group. They experienced QIXR for 15 minutes. The second group was the reading-based group. These participants read a handout containing the same content as the VR experience and also for 15 minutes. To evaluate the learning and usability, both groups completed a quantum knowledge quiz before and after the session. And in addition, the participants in VR-based group completed a post-study questionnaires, and we used the system usability scale to assess the usability of the system. In this slide, we present the results of the quantum knowledge quiz. So both groups completed the same pre and post-study quiz. As you can see, the VR-based group shows a dramatic increase from pre to post-test, with the post-study scores clustering around near the maximum. And then in contrast, the reading-based group shows improvement, but the gain is more modest. So this comparison suggests that the immersive QIXR experience better supports conceptual understanding than the conventional reading alone, and in the same amount of time. For the system usability scale results for the VR group, the SUS scores range from 75 to 100 with a mean of 85.5. This is well above the usability benchmark of 68. A score in this range is typically rated as excellent and comparable to an A grade. So this suggests that immersive interaction can make even abstract scientific content accessible and user-friendly. And here we show responses from the post-study questionnaire for the VR group. Participants rated QIXR highly across multiple dimensions, including understanding of basic concepts, graphs of qubit behavior, engagement, curiosity, and confidence. Many participants agree that the visual and the interactive elements made abstract quantum concepts more concrete. For example, one participant described the experience as like holding a basketball, and this emphasized how physically interact with the qubits make entanglement feel immediate and immersive. So overall, the feedback suggests a strong engagement and perceived learning value. This work represents an initial milestone in a longer-term XR initiative for building quantum intuitions. So while the feasibility is supported by expert review and user studies, the current system focuses on a limited number of qubits and operations. In the future, we aim to scale to more qubits and more complex simulations, including optimized performance. We do also plan to implement multi-user collaboration to support shared circuit building and social learning. And in the long term, we aim to connect QIXR with real quantum computing platforms, release it as an open source, and further improve onboarding and accessibility. So in conclusion, while quantum mechanics is often perceived as abstract and counterintuitive, QIXR leverages XR to bridge this gap by introducing an interactive, scientific-based quantum mechanics experience that is technically validated through expert interviews and technical validation procedures. Finding from our user study of 24 participants suggests that the system successfully supports developing quantum intuition by transforming complex quantum concepts into an embodied, audiovisual, and interactive experience. So looking ahead, we aim to expand the system by improving the precision of quantum state representations, incorporating more complex quantum operations, and enhancing the multi-user collaborations. Thank you so much for listening.